then this is the time to really implement. Let's make it better. And first idea is this one. Usually MATLAB creates list. I used column, so you regard this as rows. This is the first row, right? In the second row, right? And the third row, fourth row. But these are two different vectors or lists. So we create X list, right? And then P list, first stage, right? Initial stage, right? And then P list, K0 stage, K1 stage, K2 stage, K3 stage. But we still keep the name P. Then after running this, the remaining things will be, after running this, the remaining things in the P vector will be this one, this one, this one, this one, this one, and all other values are overridden, right? All these values are overridden. Then can we recycle these values to answer the question? And the answer should be yes, by changing the role. Now instead of regarding x0, x1, x2, x3, x4, the way it was, we replace the role. Now x4 is new x0. Please not right, it's not theory, but x1, x2, x3, x4. In this sense, we can rewrite the formula of the general theorem. We had this general theorem using x0, x1, x0. Do you follow me? But I can rewrite it. How? I can rewrite it. Polynomial equals f of xn, right? x4, right? Plus x minus xn, and then f of xn minus 1. Do you follow me or not? So instead of using this straightforward, I change the role. Now 0 is the top number, right? And then this 0, 1 is n minus 1. So I reverse the role. Then I can create this thing, and you will see the reason why I'm doing this. Then x minus xn, x minus. So theoretically, I didn't change very much. I just switched the role of x0 up to xn. But you will see the advantage very soon. And so on, right? So we can continue, and then finally, x minus xn, x minus xn minus 1, up to x minus x0, and then f of xn, x0, right? So essentially the same thing, right? Only change is the change of the order. But what is the advantage? Then, instead of cropping the first entries, we can crop the last entries in each. Why? Because these are not overridden in this change, right? I mean, take a look. We create a new column, then this is not overridden. If we write the new column, then this is not overridden. If we write this, then this is not overridden, and so on. Then we can just use the last result directly into this formula. So what I mean is, we can use, we can use 9 here, right? And then 7 here, and then 3 here, and so on. Do you follow me? There is theoretically no difference, but practically, you don't have to store any value. Just use 2 different vectors in the first place. X vector representing x coordinates, right? And then p vector. Then in the end, p vector will hold these coefficients. This is the key. So this is the one that you should have in your mind. After this, I will implement these things with you in 1-based index instead of 0-based index. But then let's check whether our solution should be correct or not. So I, in fact, did it. Take a look. 9, right? Take a look. 97310 should be used. So 9, 7, 3, 1, and then 0. 0 is 0. So I used. And then take a look. 2, 1, 0, right? 0 I used, right? So we can use these points. Do you follow me or not? If you don't, ask me. So we changed the row of points. x0, x1, x2, x3, but now we completely switched an xn like this. Then the next thing is the implementation. So we are creating x vector and p vector from the given problem, right? Given problem. So p and x are created this way. And then this algorithm will do the job. So let's implement. I will theoretically implement first and then do the typing later. So I will copy and paste that portion one more time and then check the meaning of each line, right? So let's do it. We should use one-based index. So x0 point is not x0 point anymore. It should be x1 point, right? So instead of x0 to xn, we should use, so instead of x0 to xn, we should use x1 to xn plus 1, right? This is the one that we should use. Now, we run this for 0 through n minus 1, then we should run this from 1 to n. Do you follow me or not? I'm changing this very carefully. And the next thing, because of this k increment, we should be careful, right? Because of this k increment. If we subtract 0, it was okay. If we subtract 0, it was okay, right? But if we subtract 1, then we may reduce too much. Do you know what I mean? So we should change it from 1 to essentially n minus new k, right? New k, k new might be better. K new minus 1, but k new is subtracting too much. Subtracting too much. So take a look. I will change verbatim first. From 0 to this one is the initial step, if we ignore it, right? This is exact copy, but now I convert it from this to, instead of this 0, because we started at one bigger point, right? So we need it. Do you completely agree with me up to this point or not? Other than k, do you completely agree with me? But if we subtract k, because of this start 1, we are in trouble because of this start 1. So we now should change it. Because if we use the same k, then we may reduce too much. So if we change things from 1-based index to 0-based index or 0-based index to 1-based index, you should be extremely careful. Then it becomes 1 through n minus k plus 1. Suddenly this change happened. Then check it. Check it. Initially, we had how many terms in this calculation? How many terms? N terms, right? And in this calculation, how many terms? Right, n minus k is a little bit vague, so let's fix k. Assume that k is equal to 0. Assume that k is equal to 0. Then how many terms? 0 to n minus 1 terms were calculated in the first place, right? Do you agree with me or not? This is an initial step. You don't agree with me? Take a look. K is 0, right? K is 0. And then I runs from 0 to n minus 1 total. N terms were used. Now take a look. We are doing the same thing, but k is not 0-based index anymore. K is 1-based index. So smallest number possible is 1, right? Then total, how many terms are there? How many iterations are there? Total 1 through n minus 1 plus 1, n, right? Total n iterations. So this is the way we switch. N itself does not change, right? So I will pause, and then you may check whether you completely understand the idea or not. Then the next thing is trivial, because all the things are okay, but this thing. If we use k is equal to 1 in the first step, already the distance is 2 instead of 1. But in the first step, we should have distance 1. So the only change that requires is this one, right? So these are the changes, and now I will summarize it. If you use 1-based index, done, right? Done. This is the chip. Or let's return back and then rewrite the part. In the previous case, n equals 4, right? N equals 4. There are total 4 plus 1 points. There are total 4 plus 1 points, right? N plus 1 point. If you don't agree with me, let me know. So let's copy the portion one more time, and then begin to code, right? Okay. So the change should be written here. So this is change, right? N equals 4. Zero-based index determined n. If there are 4 points, then n was 4. There are 5 points, n was 4. Because 0, and then total 1 through 4. because it is P, right? P1. So this is it, right? So I will begin to code after confirming whether you completely understand the change of the theory in new base index, right? In one based index. Then let's begin to program. X coordinates, right? So x is equal to -2, -1, 0, 1, 2. Do you follow me? This is it. And then P is the y coordinates. P equals -2 is used, 7, 0, 1, 2, and then 9. So y is plugged in. Now it's time to implement this first part for k running from 1 to n, right? And then for I running from 1 through n minus k plus 1, and then P of I equals P of I minus P of I plus 1 over x of I minus x of I plus k. Implementation is done, right? Implementation is done. This is, right? This is. Then let's run it. What is wrong? N equals 4, right? Excuse me? I initialize P. I initialize P. I initialize P. So I initialized X, I initialized P, and then I ran it. Then I got P row. Now let's check whether my implementation is really working or not. I should get P0 equal to 0, right? I mean P1, P2, P3, P4, P5. 0, 1, 3, 7, 9 should be obtained. Did I obtain? Done. So implementation is done. Then all you need to do is making the polynomial using these things, right? How? Very trivial. P0. Of course, you can automate this thing using loop if you want, right? But let's not worry about the part like that. So P5, P of 5 plus P of 4 multiplied by x minus x of 5, right? Plus P of 3 multiplied by x minus x of 5, x minus x of 4. Do you follow me or not? Plus P of 2 multiplied by x minus x of 5, x minus x of 4. You can automate these things if you want. Plus, so P of 5, 4, 3, 2 were used, and then P of 1 happened to be 0, right? So it's possible to write it, so I will write it anyway. P of 0 multiplied by x minus x of 5, x minus x of 4, x minus x of 3 multiplied by x minus x of 2. Oh, thank you. Right? P of 5, 4, 3. This is it, right? So one less number should be used. One less number should be used. Then done, right? Then done. What is wrong? Let's check. P of 5, 4, 3, 2. Oh, then I should use t vector, right? Sorry. So polynomial of t instead of x, right? Done, right? Oh, I see. Wow. So let's not worry about that. X equals minus 2. Done, right? In any case, I showed you. But you may program better way than this thing. So let's correct one mistake that I made. When I said the conversion, I said this thing up to 0, but it's not 0 because it's not zero-based index. First of all, it's zero-based index in theory, but we should have one less number in the first place. I will show you. So we should have n numbers instead of n plus 1 numbers. I will show you. Take a look. When we had the formula, take a look. The last thing is n minus 1, not n, right? So somehow when I just reversed, I used n, but that was a mistake. You should stop at 1, right? In theory. In theory, stop at 1, even if it's zero-based index. So in this, because of this reason, in your program, x1 is not used. x1 is the starting number. That one is not used. Right? x2 is the last thing. But in any case, you already have the idea to really implement these things in general setting. Only thing that you need to know is this thing. X equals, for instance, blah, 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 right? Minus 5, minus 2, 0, and then 5 and 10, right? So this is your x. Then from this one, you can extract n. N equals length of x minus 1, right? Done, right? And then p equals the y coordinates. For instance, what? You may pick anything. Right? So this is p. So x coordinate, y coordinate, and length all given. Then the same algorithm, right? Then you are done. Then one more algorithm doing the sum. I just type all the possible things, but you may use loops, right, to implement these things. And one thing that you can use this thing recursively. Take a look. I type this thing one time, right? Twice, right? 3 times. So you don't have to do it. You keep, for instance, product or P is used, PP thing to store this thing. Next time, PP times this thing. Next time, PP times this thing. Next time, PP times this thing in your program. Do you follow me? then you can automate this. I don't show you the automation. It's up to you. If you don't want to automate, don't automate. But problem is this. If you don't automate, then assume that you have 20 points. Then what can you do? If you don't automate, if you have 20 points. Your program may work for the specific number of points, right? But if you automate, no matter how many points are given, you can run. But if you fix or hardwire codes like this, then only for the 5 points you can run. If you increase one more point or decrease one more, then you cannot run. It's good to automate even this part. So let's pause, and then you may browse these things and ask questions. If you don't, then we will cover very, very important called splines. No question? Yes? First of all, look at the whole code. Assume that you are creating Lagrange code. What things are involved? You should create, take a look. You should create L1 through L5, right? L1 through L5. For each creation, you need these kind of polynomials. So already creating one function is harder than the whole thing in Newton's method. And speed-wise, it's not even comparable. Very fast. The Newton's method is way faster than this. So this is also for theory, right? For theory, it's nice. But for practical purpose, Newton's method is very fast. Then the next thing is very important. Assume that many of you are already engineers, but assume that you are creating some kind of curves. For instance, this curve represents a car shape, right? The side part, right? So assume that you are creating car shape. To do it, you are interpolating. So you got the data by doing some kind of experiment or research, got these points. So some engineer got like 100 points. Then if you interpolate the function, the points like this, what happens is this. Interpolate using the polynomial, and the polynomial may look like oscillation. It's not real oscillation, but oscillation is the easiest way to explain the idea. What I wanted was the curve like the above one, but when you really use interpolation, because of high order function, we have this kind of oscillation style. This is called Wang-Morai phenomenon. Then assume that you make some kind of car with this shape. It will be very rough, right? All the airs will hit your car. So it is very bad. Then what should we do? We have like 200 points that we painfully obtained. Very nice information, but if we interpolate, the car will be useless. So we are in this kind of situation. So people who never learned spline use or insist this thing. Oh, my teacher told me to create Newton's polynomial to interpolate. No, I also taught splines. Do not use high order polynomial to interpolate because of this Wang-Morai phenomenon. Spline is this. Assume that you have 4 points. Assume that you have 4 points, then you can find the cubic function passing through these 4 points, right? But assume that you have 2 points. then you can find the line, right? But now we want to add more conditions. What kind of conditions are possible? The Rublev condition. In other words, we know x1 point and then y1 position. We know x2 point, y2 position. We know x1 position and then y1 slope position. Slope number, right? Y2 position, x2 position, y2 slope number. In other words, instead of just connecting the position points, we are also using the same slope. So this is the idea behind it. So before going to full spline, I will explain this direction briefly. And the idea was developed before, and let me briefly mention. This kind of polynomial is Hermite interpolation. In other words, assume that xi, yi informations are given, right? Then we can use this kind of information to find the polynomial. But assume that we have more than just height, the slope, then we can have a better curve. So this is the idea behind it. And I will show you using this case. So instead of using xi, yi, let's use numbers. First point is 1, second point is 2, right? So 1 and 2 is the point. And first height is 5, second height is 6. First slope is 2, second slope is 3. So we are using numbers instead. Then can you find the function satisfying these 4 conditions or not? Idea is this. Let's say y equals a0 plus a1x plus a2x squared plus a3x cubed. Then how many unknowns should be determined? How many? How many unknowns should be determined? 4 unknowns. How many equations can you obtain? We have 4 equations, 4 unknowns. And we can solve this for these 4 unknowns. So let's do it. A0. So I'm plugging in this number, right? These 2 numbers. A0, A1 times 1, A2 times 1 squared, A3 times 1 cubed equals 5. Do you follow me? Similarly, A0 plus A1 times 2 plus A2 times 2 squared, A3 times 2 cubed equals 6. Now, the derivative is required, so let's differentiate. Derivative says 0 times A1 plus 2A2x plus 3A3x squared. Then let's plug in. 1 is plugged in. Then A1 plus 2A2 plus 3A3 equals 2. Right? 2. And A1 plus 2A2 times 2 plus 3A3 times 2 squared equals 3. So we have total 4 unknowns and 4 equations. So it's a linear system of 4 by 4, right? So you can solve this system for A0 to A3. So this is it. Then it's not me to solve this thing. It's the MATLAB that should solve this system. So A matrix is 1, 1, 1, 1, and then 1, 2, 2 squared 4, and then 2 to the power of 3, 2 cubed, right? 8, and then 0, 1, 2, 3, and then 0, 1, 4, 12. This is the A matrix, right? Do you follow me? I implemented the left side matrix. And then right-hand side matrix should be 5, 6, 2, 3. Do you follow me? Then let's solve it. Negative 4, 19, right? Negative 4, 19, negative 13, 3. So I will write it. Negative 4, so these are the numbers that we obtained. Do you follow me? So the polynomial is this one. Negative 4 plus right here, right? This is the polynomial. So let's use better space. Let's write it here. Y equals negative 4 plus 19x minus 13x squared plus 3x cubed. So I will implement this function. So y is a function of x, and then minus 4 plus 19x plus minus 13 times x squared plus 3 times x cubed. Then let's calculate y of 1. Y of 1 should be what? Take a look. Y of 1 should be what? 5, right? Y of 2. Y of 2 should be what? 6, right? Now let's differentiate this function. Will this work? It may not work, right? Will this work or not? It's not symbolic. It may not work, right? So let's differentiate by hand. Y primed is what? Y primed is 0 plus 19 minus 26x plus 9x squared. So I will implement y derivative, right? So y derivative function equals 19 minus 26 times x plus 9 times x squared. And then y derivative of 1 is, y derivative of 2 is 2 and 3, right? So I completely obtained the polynomial passing through 2 points and then having specific derivative assigned by the problem. And I completely showed you the point, and please browse the idea and ask questions, because spline is very close to this idea. In any case, we can generalize. Oh, then can we make it better? Of course, we can make this way better. How? Not just the first derivative of information, y1, y1, second derivative, third derivative, right? Fourth derivative. All these things can be given, right? All these things can be given. Then we can have better result. So this is called Hermite interpolation, and there is even formulae related to Hermite interpolation. How? This is the formula. Assume that this derivative information, first derivative, not second, but first is given. Generalization is possible. xi, yi, first derivative, second, third, any things can be given, right? But assume that we limit this information to just first derivative. In other words, we don't have second or third or fourth. We just have these things, right? X position, y value, y derivative value. Then we can even make a formula like this. And as you can see, H is not beautiful. H looks like this. L is what? Lagrange polynomial. the Lagrange polynomial should be differentiated. This polynomial should be differentiated. Then logarithmic differentiation might be necessary. Because of this reason, you don't have to use the formula to solve the problem. You can do hand calculation or MATLAB calculation like I did, right? If you want, you can create the formula using this, right? But I don't ask you to do. It is suggested, but it's not the requirement. You can find the polynomial any way you want, especially following my style is okay. Then let's follow the notes. As you can see, Runge-Murray phenomenon, like oscillating thing, happens if you use higher order polynomial. So what we do is piecewise polynomial. In other words, we use some kind of polynomial, Lagrange piecewise, or Hermite, or spline, these kind of things. Then let me know. Let me know whether you learned about spline before. Have you ever seen spline ruler style thing before? Have you ever seen spline ruler style thing? It's like some kind of, it might be sold at, like, right. So there is some kind of tool. You can sketch curves. You can make curves using the shape, and then shape stays, and then you can curve. But in any case, piecewise polynomial has this idea. If I use just one piece to interpolate many points, right? If I use just one piece to interpolate many points, then it's inevitable to have oscillating style thing, right? It's inevitable, right? And now, I do not interpolate by one piece. I just connect this piece, right? I connect this piece, I connect this piece, I connect this piece, and so on, right? So this is called piecewise approach. So it is one piece approach, right? And piecewise approach. What is better? For lower order functions, global approach is nice, right? Like up to fifth order, global approach might be good. But assume that you are handling 12 points. Then at least 11th order polynomial appears if you handle globally. It's not a good idea. So in the case, we need to use piecewise polynomial. In other words, you connect piece by piece. Then, oh, some engineer got an idea. Now I have all the nice points to design the car, and let's connect. So I will do it. And then made the car this way, or I made the shape this way. Will it work? That's true. So, first order function doesn't work. Then, let's use second order function. Let's do it. Will this work? Impossible, right? So first order function or second order functions cannot make smooth edge. So the minimal requirement is cubic spline. If you use cubic spline, it will be smooth. The minimal is cubic. Why? First and second cannot fly. As you can see, always this kind of sharp edges or things. Cusps, right? So there are rigorous definitions of spline and so on, but let's not worry about rigorous definitions. All I want is this one. Assume that a certain number of points are given at any shape, right? Like this. Then, can you connect this very smooth? And the answer is yes. And you should do it. So it connects somehow. These things very well. So there is some curve like this. You will do it. Then let's break up. This is, I will follow the book so that you can directly copy this part in the code. All the theories here are for this thing. And what I used was zero-based index, right? Zero-based index. Zero-based indices are used. So x0, x1, x2, x3, x4, x5, x6. Then, how can we create a spline passing through these things? First of all, is the spline unique? The answer is no. There could be two different smooth curves interpolating the same set of data. So it's not unique. Then how can we impose restriction to make a certain spline unique? That kind of thing will be mentioned. Then let me check. The spline should pass through the given points. And how can we make a polynomial, cubic polynomial here? Cubic polynomial here. And this kind of thing should be satisfied. At this point, x1, it should pass through the same height, right? From this side, right? From this side and from this side, it should have the same height. Do you agree with me? And it should have the same derivatives. And second derivatives. And you can impose more if you want, but you generally, up to this point, is required. If you don't understand, ask me. So we are making the curve very smooth. To make the curve very smooth, at the same point, from one side and from the other side, we should have the same height, slope, second derivative, and so on. The more, the better. But if we ask too many things, then the calculation may be too complicated. Because of this reason, mostly splines require about y first and second derivative matching from left and right. So we do the same thing each line, to each point, right? We do the same thing to each point, right? So we now attach. So at each point, these things should match. Then, what things should we handle? Assume that we find a cubic polynomial here, and the cubic polynomial here may have this form, this pattern. Right? Cubic polynomial in this interval have this form. Cubic polynomial in this interval may have this form. Do you follow me? And then we should have matching numbers at xi. So if we plug in xi here, then they should be equal. So we should have this situation. A plus bxi plus cxi squared plus bxi cubed equals p plus qxi rxi squared plus wxi cubed. Do you follow me? And then derivative. B plus 2cxi plus 3dxi squared should match, right? Q plus rxi times 2 plus 3wxi squared. And then second derivative. 2c plus 6dxi equals 2r plus 6wxi. So you should solve a system like this from the leftmost point to the rightmost point of the given problem. Then, how many equations will you have? How many equations will you have? Roughly to determine 4 unknowns. Roughly to determine 4 unknowns. 4 equations, total 8 equations, right? And so on. But it's not easy. Assume that you have total 1 plus 10 points, total 11 points. Then how many equations do you need? In this approach, we have total 10 subuniverse, right? We have total 10 subuniverse. For each subuniverse, we have A0, A1x, A2, x squared, A3, x cubed is required, right? For each subuniverse. We have total 10 subuniverse. Then how many unknowns should be determined? For each universe, how many should be known? 4. There are total. Then total 40 unknowns should be known. Assume that you are interpolating some kind of surface, then you may have 20,000 points. If we follow this approach, then total 40,000, 80,000, right? 80,000 unknowns should be determined, right? To determine 80,000 unknowns, generally we need 80 by 80 matrices. It's huge, right? So this approach is okay, but in general it's very unusual. Then, what things did mathematicians develop? That is the one that I want. So if we follow that kind of approach, if you want to determine AI plus BIX squared plus CIX and then BIX cubed approach, we have no hope. We have no hope. So what mathematicians did was this thing. Break up the domain. Of course, this is given by the problem, right? x0, x1, xn minus 1, and then xn, right? So it's broken up by the given points in the problem. Then, mathematicians try to find the second derivative m1 representing y1 second derivative, right? So first point, first inner point, second derivative is called m1. And second point, right? Second point, second derivative. It's called m2. And then third point, and then m3. You follow me? So m3 is the second derivative value at the given point. So we collect these things. So total m1 through mn minus 1 inner second derivatives are required plus boundaries we impose. Boundaries we impose how? To make it simple, we impose boundary like this. Let's call the second derivative at the boundary 0. The boundary second derivative is 0. It's inflection points, right? These are inflection points. So we impose the conditions like this, and then we solve this reversely. So what is the thing we do? We find the relation between mi, right? In other words, we find some kind of matching numbers for mi, and then because of this relation, we create a system to solve m1 through mn minus 1. So we create a system like this. So from the relation of mi, we create a system like this. And then it's a linear system. Can you solve this linear system? The answer should be yes, right? So if we solve this linear system, m1 through mn minus 1 is solved, right? For instance, 1, 2, 5, 0, 3, and so on, right? We may find this. Then from these things, we create this cubic polynomial. So this is the approach. Then what is the advantage of this approach? You don't need 4 times n equations. You don't need 4 times n equations. Total how many? Just n minus 1 equations to determine m. Once m is determined using m, we can assemble the spline. This is the approach. So I will pause, and then you may check whether you completely follow or not. So instead of determining 4 unknowns for each subinterval, we determine the second derivatives at given inner points. And we impose boundary conditions, such as zeros. And then we solve this for m1 through mn minus 1, total n unknowns, like 20,000 unknowns instead of 40,000 unknowns. And then we solve 20,000 by 20,000 problem instead of 80,000 by 80,000 problem. So this is the approach. And please browse the next question. I will show you the actual formula. So take a look. Initial setting is this. I will let you know what those symbols mean. Initially, this is x1, right? And this is y1, right? And then this is x2, and this is y2, and so, right? And this distance has a name. So let's check it. I will show you. This distance has a name. Take a look. It uses this index. It uses this index. So this is h1. This distance is h1. And then this distance is h2. This distance is h3. Do you follow me? So when you see x or y, all given by the problem, right? X and y are all given by the problem. H is nothing but the difference. So let's check whether you have all the necessary ingredients. This is it. So you now understand the situation. Points are given by the problem, right? These are given by the problem. These things are given by the problem, right? All these are given by the problem. But now, once these are given, then you assign xi, yi, right? You assign xi, yi. And then you assign hi, h1, h2, h3. After this, now I will show you the full description. Show you the full description. We set the second derivative at the boundary equal to 0, right? Second derivative at the boundaries equal to 0. And we want to determine unknowns representing the second derivative at inner nodes, right? Inner lows. m1 through mn minus 1. Then, by the relation, we can get this kind of system. we can get this kind of system. Then take a look. Can you determine H0 or not? H0 is what times 1 minus what? X1 minus X0, right? H1 is what? X1 minus X2 minus X1. And then you can determine. So you can determine everything on the left side. Take a look. Is there anything that you cannot determine? Take a look at the right-hand side. Y2 is given by Y1 is given. All these are given by the problem. H, nothing but the distance. So all these are given. So given, then you can solve this system for M1 through M minus 1. Please browse and let me know. Of course, why? If you want to know why, please come to my office. I will spend 2 hours with you to show you how it works. Or if you don't want to come to my office, I can give you a copy showing this part. In any case, by solving this system, we can determine M1 through M minus 1. Then, how can you make splines? How can you make splines inside each interval? In other words, what is the spline here? So I want to know the equation of the spline in this domain. And I want to know the equation of this function in this domain. And I want to know the equation in this domain. So how can I know the equation in this kind of domain? So I will show you. These are determined here. So take a look. If you cannot determine some terms here, let me know. Mi is calculated by what? By solving this term, Mi is calculated. Now, take a look. Xi is nothing but nodes, right? Given by a problem. Mi, by solving this. Mi plus 1 by solving this, right? Xi, Hi. So is there anything that you cannot determine? All these can be determined for the given subinterval xi through xi plus 2. So for each subinterval, you determine the polynomial, and polynomial. And then later, sketch it from leftmost point to the rightmost. But this is not one piece. You should sketch small pieces and then assemble. While in MATLAB, you determine the vector and then later attach the vectors or do something that you can do to make nice spline. So this is the theory behind it. And I will pause and then you can browse the idea one more time and ask questions if you don't. And I will cover the other possible cases. As I mentioned, splines are not necessarily unique. M1 is the second derivative at x1. So x1, x2, x3, there are points. So there are points. Then, for instance, this is xi position, right? Then xi position has yi second derivative, right? This is called mi. But we don't know the second derivative yet. That's the reason why we should solve this system to determine second derivatives at the specific nodes. I just name the second derivative mi. Okay, we solve right, mi, right. So please browse top to bottom and check whether you completely recognize everything in this page or not. And a few things and then we'll finish. The problem is this. I set two end boundary second derivatives equal to 0. But why should they be equal to 0? It could be different, right? That's the freedom. So by changing these things, you can create different spline by changing these things. And you can do many things with that change. And one famous case is this one. Instead of just fixing the two boundary positions with second derivative equal to 0, let's ignore. In other words, let's not determine. But impose this clamp condition. Then we add these two lines. We add these two equalities. So first derivative at the first boundary and the first derivative at the last boundary, right? These are imposed. Then it's called clamp boundary. And the spline that is created by this is different from the spline that we created from the previous one. So there are names. I will briefly return back and then show you the name. So if you create the spline using this, natural boundary condition, right? But if you create the boundary with this condition, then it's called clamp. So you should see the difference. Here, M0 and Mn are zeros, right? Here, M0 and Mn are not necessarily 0. We don't know. We don't know, right? M0 and Mn are not known until we have solved this system. So this is the difference. But essentially, they look very similar, right? To the formulation or setting up, they look very similar. And if you cannot determine some value here, please let me know. Take a look. Is there any value that you cannot determine? H is the distance between two nodes, right? Done, right? H or H, right? Done. Y given by the problem, H given by the distance, Y prime to 0 given by that, right? Y prime n given by. Then spline formulation is very similar, right? Spline formulation is exactly the same. This is the way to determine the spline. Once you determine M, then you can determine spline. You mean this boundary? No, this has no relation directly with. In this sense, it had a relation, but in no direct way. So I will explain the situation. Assume that you are finding splines from this point to this point. Assume that you are finding splines, and then you have some kind of data points, right? So you are finding this kind of thing. But somehow, you have strong conviction that this slope should be 2, and strong conviction that this slope should be 5. So assume that you have this kind of strong conviction at the given points. Then you can impose y1 prime equal to 2 condition, yn prime equal to 5 condition in the formula that has indirect relation with m0 and mn. So you impose this condition and this condition. I said 0, right? So if you have some strong idea about the boundaries, in other words, boundary slope should be this or that, then you can impose the condition. That is called clamped. In other words, because I'm not working out of blue, just you can check whether my slope may have like 4 or 5 or 2 or 0. I know, right? And I know. And impose the condition. Any other questions? Then let's stop here. And next time I will mention about a few more ways to improve it